I can't hear.
Can you hear Karin?
Can you hear? No?
Now we can hear you, yes.
Okay.
Not see anything yet, but hear you, yes.
There is an almost empty blackboard.
Well, but we only see.
No, I was joking, sorry.
Okay, I think now it's okay.
Mm.
Okay, so it's my pleasure to introduce the last speaker of today. That's Karin Baur from the University of Leeds, who will tell us about orbifold diagrams, dimer quivers, and associated categories. And Karin, if there are questions in the room, if you wouldn't mind repeating them, that would be fantastic.
I will try to remember.
Thank you.
Okay. Yeah, thanks a lot, and thanks to the organizers for inviting me. And it's great to do a Blackboard talk now instead of the many Zoom talks, but you will see that it's a bit difficult with that topic because it's easier to draw pictures on my iPad and just copy them over. But yeah, so I want to talk about orbifold diagrams, associated quivers, and algebras, which for short I call dimer quivers, and associated categories. And that's joint work with Andrea Pasquali and Diego Velasco. And you can find it on the archive at 2010 13182. Okay, so alternating strand diagrams were introduced around 2005 by Postnikov in the study of the Grassmannian. And for example, there are sources for clusters in cluster algebras or cluster tilting objects in cluster categories. As we've seen in some talks during this program already, originally Postnikov drew them on a disk with points on the boundary, but you can do that more generally. And for example, also Goncharov's webs are a generalized version of that. And today I want to look at another direction, introducing orbifold diagrams. So sort of, if you want to start on a disk and you have a symmetric diagram under rotation, you might think of taking a quotient. But I'm going to start directly on the disk and set it up independently and then see that this commutes. Okay. The motivations for that was work of Pasquali on symmetric Postnikov diagram and work of Labadini, Fragoso, and Velasco on disk with orbifold points of order 3. So what do I mean by an orbifold diagram? So I want to have a collection of oriented curves on some disk. And I call the disk sigma n. It has n mark points on the boundary. And then there is an orbifold point of some positive I call that omega orbifold point of order d larger than 1. I might just assume it's at least 3 for some technical details. And I want to have a collection of curves linking these n mark points, and I call them strands, as Postnikov did. So such a diagram consists of n curves. Which are called strands. They should never go through omega. And they connect these points. So they introduce a permutation of the points. Say Ci goes from I to tau of I, or tau permutation of the points. You can have fixed points, and omega should not be contained in any of the curves. We all take this up to moving around a bit, so but you never want that to go through. And we call that a weak orbifold diagram. So this is a weak orbifold diagram of type tau. If the conditions, the following conditions are satisfied, we have finitely many crossings which are of order 2 and transversal. So they should be transversal multiplicity 2. And they should also alternate as in the alternating strand diagram picture. So whenever you walk along a strand, you see the others coming from alternating directions. So that's first.
Karin, excuse me for the interruption, but could you halve the board so that you write first on the left side and then on the right, because then I think it's easier for us online to see.
Okay. And then you might see a picture which is not allowed in the simple disk setup, but in more arbitrary surfaces. Whenever we see two curves which look parallel, then we want that the orbifold point is inside. Or if you see a self-intersection, again, you want that the orbifold point is inside. So these configurations locally must contain omega. We just write the cross usually and omit omega. Okay, so that's the minimal condition set, but we need a little bit more. That's why it's called a weak orbifold diagram. And this collection should be called O, which I forgot. I use calligraphic O. And then O is an orbifold diagram if furthermore the D is, well, like right now you see the D didn't play a role. The order of the orbifold point wasn't involved anywhere, but there's an extra condition, so it has to be in a way that when you try to symmetrize it, you don't get forbidden things in the Postnikov setup. So these are the condition. The condition translates into if D is larger than the maximum of two combinatorial conditions. So the maximum over S of C, I'll explain what that is. See some curve in the diagram and the maximum of a pair of different curves over any pair of different curves L of C1, C2. Okay, what does this do for S of C? I have to look at any curve self-intersecting. For example, I have a point P, this is one of this 1 up to N, and then the curve does something like that. Then I have to look at subcurves. How often do they wind around omega? So S of C is the maximum of point over all the points in the self-intersection of C. And then you look at the winding numbers and then the absolute value. W is the winding number. And then for the L, we look at pairs of curves. So some pairs of curves will form as a closed loop again because they meet twice. Let's have one like that and one like that. So if this is C1 and this is C2, And then I should look at points which are in both on C1 and C2. So L of C1, C2 is the maximum. Well, you look at subpaths which form a closed loop. So here I could go along C1 and then backwards along C2. And then I look at the winding number. So I take the winding number of C1 tilde, C2 tilde inverse, again the value, where C1 tilde and C2 tilde would be between 2 points of intersection. So Q1. Okay, so that's the definition of an orbifold diagram of a given permutation. And I've drawn some pictures. Okay. And I hope you can see the colors. So O1 has 3 points on the boundary, which I usually do clockwise. The blue curve C2 goes back to itself. The purple one goes from 1 to 3, and the red one goes like this. So the permutation is 1, 3 in that case. The other two have permutation identity. So that's fine. And in fact, I will prefer those later. I guess you could check. So there are some interesting things happening here where you can really compute L and S and see that these are all 3 orbifold diagrams. I should say what the order is, otherwise it doesn't work. Or either you work it out and take the minimal D that satisfies, or what did I choose? I think the middle one had 5. That was actually necessary because I found 2 curves which give a 4. The first one is 3 and the last one is 3. Okay. Okay. Well, properties. So the first one I've already mentioned. If you take this definition of an orbifold diagram with tau and orbifold point of order D, then you can take the default cover so the order of omega. Then if you take the symmetrized version of O is a Postnikov diagram. That's just by definition. And here I really want to have D larger than 2. So that's where I need it. And then you can go back. So if you take the symmetrized version of some O, then you will have a D-symmetric picture, which is, I mean, invariant on the rotation by 1 D. So you can take the quotient again. I'm not going to use that later, so, but I think it's clear what that means. You recover O. Similarly, if you start with a Postnikov diagram, which is symmetric under some rotation, then you can take the quotient first and symmetrize, and you get it back. It's well behaved. And the goal is that we associate to these diagrams some quivers and path algebras, and then categories of modules. And also to each of these diagrams, I can associate a collection of K subsets, and we'll get some maximal rigid or cluster tilting object. That's the idea. Like in parallel to what you can do for the Grassmannian cluster categories as introduced by Jensen-King-Su, where you can use, for example, the Postnikov diagrams from Scott's paper and get cluster tilting objects. Okay. As in my work with King and Marsh. Okay, so I should say how these quivers look like. So it's going to be a quiver with potential QO and WO. The vertices of QO will come from the alternating regions. It's really not going to work. If you look at an orbifold diagram, as in the Postnikov diagram, you will have alternating regions and oriented regions. For example, these regions here are oriented clockwise or anti-clockwise. And all the others will be alternating. So we put vertices, alternating regions. And now there's a new feature. You see in the last picture, the orbifold point is in an alternating region. So here I have to take into account that I really have D copies of that region. Whereas it's different in these two examples. So, and D vertices if omega in such a region. And then arrows come from the strands. So in the quiver, I would have vertices in the alternating regions, and then I orient the edge according to the orientation of the strands. So that's basically what it is. If omega is in an alternating region, we get D pairs of, no, well, D paths going through in parallel. So let me do that. Here we had order 3 and omega was in an alternating region, so I have to draw D vertices for that region in the center. And otherwise I get alternating regions like on the boundary, like these 3. And I use the orientations of the strands to draw the quiver. Like that. I'm just going to copy my notes. Oh, that was wrong. And in the center, yeah, so each of them behaves in the same way. So I get 3 paths, D paths going through these D copies. Now, if you see outside the central region, this is just a quiver with faces as in the work with King and Marsh. So basically you have a bunch of oriented cycles which are glued together in a nice way. And you know that everyone, and you alternate between positive and negative and positive and negative. But, and so that would be the case in these. But in that one, in the middle, you have D disks, which are all like D quivers, which are isomorphic and just glued on an annulus. Yeah. And I'm running late. I try to be a bit faster now. So what is the potential? Well, you have to take cycles, these fundamental cycles, because I said the quiver basically has a lot of oriented disks, which are my fundamental cycles. And outside the central part, so there in the central part, there would be one oriented region or the D copies. So outside the central part, I just do the usual thing. I take sine of C times C, C not around omega. And then for the central part, either I take 1 over D sine of C, C0 to the D. If omega is in cycle, so in the left two pictures, omega is in an oriented cycle, which I call C0. And if not, I have to take some sum, which involves taking powers of the primitive d root of identity. So I don't want to spell it out, but I just want to make sure that you see there is a potential in each of the cases, and that you have to distinguish the two cases. And you have R summands here, because depending on the size of that alternating region, here it was 2. If it's R, which is even, you will get R cycles going through. I mean, so here I have one kind of cycles on the right and one kind of cycles on the left of the VIs. Okay. And that potential is the same as appears in work of Giovannini and Pasquali and Giovannini, Pasquali and Plamondon. I'm to changing, I mean, choosing the Xi carefully. Okay. So if we have a quiver with potential, then we can use the potential to get relations. We take the cyclic derivatives of the potential, which means whenever you have an arrow between two faces, you will say going back in one direction is the same as going back the other direction, basically. So now we want to get algebras. And AO is the frozen Jacobian algebra of QOWO. And which means these relations that you get from arrows only come from inner arrows. When an arrow is between two cycles, you use it to define a relation, but at the boundary, we don't do anything. That's the frozen part. And you can do boundary of that. So that's going to be EAE for E. The sum of the boundary idempotents. So in the quiver, you just take paths which start and end at the boundary vertex. And then with this, we can state our main result. And then we'll try to explain. I hope that still works. It does. So that this algebra A is the endomorphism algebra of a cluster tilting object. Which means there must be an algebra which I can define without the diagram. And there must be a way to associate modules to the diagrams. No, save time. Okay. O is an orbifold diagram of Grassmannian type. I know I have to explain what that is. I'll do. Take M to be D times N. So N was the number of vertices on the boundary. D was the orbifold order. And K W plus times N. So Grassmannian type asks for the permutation to be the identity. So tau is the identity, and there exists. I don't know where I should put that. Yeah. Yeah, I'm just going to say. Every strand has winding W plus or D minus W plus around omega. So for some W plus between 0 and D, and well, I'll let you figure out the W pluses here. So that's what I want. The point is, in that setup, if you look at the symmetrized version, is exactly a Postnikov diagram where the permutation is I goes to I plus K for that K. Yeah, and then I can say okay, I switch notation. So that's AO. From there, this is isomorphic to the endomorphism algebra for some algebra B and TO. And I know I will define this, which depends on N, K, and M. And now it's good we have two sides. So how is B, N, K, M defined? Well, we've seen, no. Now, you know, M is much larger than N. Well, M is a multiple of N, D times N. And I really want the smaller one here. So we take this double cycle, or this cycle with Quivers arrows in both directions. As we've seen a few times, arrows xi, yi, and then B and Km is defined as the completed path algebra of that quiver, comma n, by the relations x, y minus yx, and x to the k minus y to the m minus k. Okay, so far, when we've seen this kind of picture, it was always the same n. But what it means is here I take much longer paths with y. So I go around a few times because my d was at least 2 or 3. So the algebra we've seen, which is in the paper by Jensen-King-Su, has n equals m. You take a completed version of that. So that's the algebra. And what is TO? Can someone tell me how many minutes I have? Like 2?
I think technically 2.
Yeah. Okay. I'm not surprised. So TO is a direct sum of rank 1 modules for this algebra. So you have to look at the diagram, you have to collect subsets, and you take a module for each of those subsets. I'll explain this in a bit more detail. So, but that's sort of the first part, and as a corollary, the boundary algebra of O is isomorphic to B and Km. So that recovers. And I should say these algebras are Morita equivalent to taking the skew group algebras of the ones for the Postnikov diagram with the Grassmannian permutation with the cyclic group given by the order D. But, okay, so for the modules in the last 1 minute, modules. But to get the labels, I've written the labels here for that quiver. So the idea is that you introduce a cut between 1 and n, and then you go along a strand. I'm not only going to do it for strand 1. You put the label 1 here, and whenever you cross the cut, you either add n or subtract n, depending on the orientation. So here I cross the cut, then I get n was 3, a 4, and I cross the cut, I get an n is 7. And then I put labels on the left in alternating regions. You should find that the central region gets 1, 4, 7. Okay, that's one part, and then the modules. So I've tried to indicate the rank 1 module picture in a similar way that you can do visualize rank 1 modules in the Grassmannian cluster category as defined by Jensen-King-Su. So that module has labels 1, 2, and 7 for n is 3 and the big M is 9. So really you see 1, 2, and 7 on the picture here. 1, 2, and that should be 7. But then you split it up in levels coming from this threefold orbifold point. So there's one at level 0, one at level 1, and one at level 2. And if you went and added, so I wrote what is it? Equivalence classes. If you add 3 to each label, you get 1, 4, 5, which means you shift the levels by 1. So the modules now look different, but you basically get B many, unless you're in the central point where the orbit just has one element. And they are isomorphic, but come from different pictures. So that gives you a cluster tilting object in that category. Thank you.
Okay, are there any questions?
There's a question here.
Okay.
You said right at the beginning that you wanted D to be at least 3.
Yeah.
Why not 2?
Is in some of the examples, I think in this one you would, well, in some examples you would get an alternating region of size 2 in the symmetrized version. And an alternating region of size 2 is exactly a lens which you want to avoid.
Oh, I see.
Yeah.
Okay.
That's,
okay. Thank you.
yeah.
There's another one.
Hi, thank you. I wonder if you could say anything about the proof. Is this a direct proof, or do you use ideas from BKM?
We use some ideas. We also use a lot work by Pasquali, Giovannini and Pasquali, and that we have this Morita equivalence. So we use the skew group algebra and describe exactly, well, really a functor between, I don't know how we called it, the BKM, and then you take, so I assume that I have a group, finite group action on this, because I always have labels which are going to be invariant. And so this gives me a functor to the skew group algebra, and then I can use that.
Okay,
But so
great,
it's a bit
yes.
more by foot, I think. So we don't
Mhm.
use all this constructing explicit homomorphisms. Yeah.
Great, thank you.
Mhm.
One more here.
Sorry, maybe just following up on that. So if the sorry, long day. Do you think if you can just substitute out, you'll use the proofs from BKM in the case that D equals 0 for Grassmannian type. If you have the corresponding statements for non-Grassmannian type, D equals 1. Sorry, not 0. D equals 1. You think you just plug those into your proof and you
That's
drop the
possible.
Grassmannian
Yeah,
type
that
or
would be
something?
one of my questions. What do you do with non-Grassmannian types?
Okay.
Because we haven't continued looking at that.
But you think
it
you use
could-
this assumption in a fundamental way other than by citing BKM?
No.
Okay.
Yeah.
Okay.
So it would be interesting to see what other cells are.
Yeah.
And but the other thing which comes here is really how to describe this because we look at CM, BKM, like the gene variant cluster tilt to get this gene variant cluster tilting object, but I cannot say this is the category of Cohen-Macaulay modules or something.
Right.
That would be nice to have a direct. I have no idea.
Mm-hmm. Okay, thanks.
So I think we can pass to the virtual people.
Okay. So I think there are no more questions in the room, and I don't see any questions online. Well, in this case, let's thank Karin and indeed all the speakers of today. And we will resume tomorrow at 1 o'clock. Okay. Bye-bye.